Hi everyone, today we are on page 20, let's see, hang on, 27. And we're taking some more notes about binding energy and stability. I guess we didn't talk about binding energy last time, but more stuff about nuclear stability. So, first thing we're going to write down is there is something called binding energy. And this is, the technical definition is that it is the energy that you would need to put in to separate all the protons and neutrons in the nucleus. So it's basically the energy to disassemble the nucleus, to pull it apart. Okay, so since the binding energy kind of measures how strongly the nucleus is held together, we can say that a higher binding energy is generally going to be a more stable nucleus. So the higher the binding energy, the more stable the nucleus. Okay, to explain a little bit about where binding energy comes from, I want to talk to you about some forces in the world in general. There are 4 forces. Okay, so there are 4 forces through which matter interacts. So one of them is gravity. So you know things that have a lot of mass attract other things. One of them is called the electromagnetic force. And this sounds complicated, but this is just like things that are positively charged are attracted to things that are negatively charged, that sort of thing. Then we have the strong force, very creative name. This is the one that is associated with the binding energy. So it helps hold the nucleus together. And it is a little bit more complex to explain. It comes from interactions between particles called quarks that are what make up protons and neutrons. So it's a little bit more complicated to explain. And then there's also a weak force. But the strong force is the one that has to do with the binding energy. Okay, so in your book, I just want to show you a graph that you're going to be looking at later today in an assignment. It's this graph. So this graph shows us the number of nucleons. Remember, that's the protons and neutrons. So the number of nucleons in the nucleus, and then the binding energy is over here. So you can see the binding energy goes up as we get more particles in the nucleus, and then it kind of starts to go down. And remember, higher binding energy is a more stable nucleus. So more stable nuclei are going to be kind of up here because they have the highest binding energy. Okay. There's another graph that we're going to look at in class. You can see it right here. This graph is called a band of stability graph. So we've got the number of protons down here on the x-axis and the number of neutrons here on the y-axis. And if you can see this black line right here, any nucleus that is on this black line is stable. Anything that's like above it in this gray part over here or this gray part over here is going to be unstable, and it's going to give off some kind of radioactivity. And the different colors kind of tell you which type of radioactivity it gives off. So for example, a nucleus with 14 protons and 14 neutrons, that's right here, that's stable. But a nucleus with 28 protons and 50 neutrons, that's out here, that's unstable. It's going to give off radioactivity. So you're going to be looking at that graph today, and I wanted to just show you kind of what it looks like. Couple other things we need to write down that have to do with stability. There's something called half-life, and we'll talk a lot more about half-life, but what it is the time it takes for half of the atoms of an unstable nucleus to decay. So if some sample is radioactive, the half-life is how long it takes one half of that sample to decay. So if I have 10 grams of carbon-14 and the half-life of carbon-14 is about 5,700 years, after 5,700 years that 10 grams will now be only 5 grams is radioactive, and the other 5 grams will no longer be radioactive. And we'll talk a lot more about that later, but what you need to know right now is that if elements have a long half-life, they are more stable. They're still radioactive, but they're more stable than something that has a really short half-life. Okay, I'm going to show you a chart in your book again. So here are some half-lives. The most stable isotope listed here is uranium-238 because it has a half-life of 4.5 billion years, and we know that a long half-life is stable. The least stable isotope listed here is going to be carbon-16. It has a half-life of 0.74 seconds. So that's super, super short. So it's not very stable. It doesn't stick around very long. It turns into another element pretty quickly. So that is stability and half-life and nuclear binding energy.